Welcome back everyone. In the last lecture we have seen the response of a standard second order system. We saw how the output changes depending on two main parameters called the damping ratio and the natural frequency of the system. Today we will start from that point where we ended last lecture. So, this is what the step response look like. For zeta equal to 0, we had an undamped response. For zeta from 0 to 1, we had a underdamped response. For zeta equal to 1, we had a critically damped response, and for zeta greater than 1, we had an overdamped response. Today, we will try to relate these responses with the poles of this second order system. Look at it, look at the transfer function of the system. So, if I ask you what are the poles of the system, you will have to find out the roots of the denominator of this, which is a standard second order polynomial, and you know how to find out the roots of a second order polynomial. So, in this case this will turn out to be minus zeta omega n plus minus j omega n root over of 1 minus zeta square. Okay. So, you can go ahead and solve this equation. I am not going to do it for you because this is a very standard second order polynomial, and this is second order equation that you have. So, you know what the formula for finding roots of that, and you can directly find out the roots of the second order system to be of this form. Now, we will check for each of these cases, undamped, underdamped, critically damped and overdamped, how does these pole change. So, let us get started with that. So, let us start with the case of zeta equal to 0. Now, if zeta is equal to 0, notice the real part here becomes 0 and the imaginary part, the purely imaginary part, the square root here becomes root over of 1, which means the poles are at plus minus j omega n. Okay. And so, if you draw it in the complex plane, as can be seen here, it will be on the imaginary axis. The response we had seen in the last lecture itself will be a sinusoidal response of this form, or a cosinusoidal in other words, because it is 1 minus cos of omega n t, and you see the frequency of this oscillation of the response would depend on the value of omega, and that is why we gave it the name natural frequency. Now, let us go to the case of underdamped response where zeta is between 0 to 1. Now, if zeta is between 0 to 1, you will have these two roots, and notice that since zeta is between 0 to 1, both the roots will come out to be complex conjugates of each other, as you can see in the plot here. Okay. Of course, this has no zeros, so I am not plotting the zeros, only the poles I am plotting. The poles looks like this. An important thing to note here is that the magnitude of the real part is zeta omega n, and the magnitude of the imaginary part is omega n root over of 1 minus zeta square, which is nothing but omega d, right. If you remember, we had defined this term omega d, and that was called the damped oscillation frequency, right. So, omega d equal to omega n root over 1 minus zeta square is the imaginary part of the complex poles. One more important thing to note here is that if you draw a line from the origin to these poles, this angle will come out to be your phi, because notice that if I find out cos phi in this case will be what? Cos phi will be equal to, so you will have zeta omega n divided by the magnitude of this hypotenuse, which will come out to be root over of zeta square omega n square plus the magnitude of this part, which is omega d square, which is nothing but omega n square whole of 1 minus zeta square, and you can see that this will come out to be zeta omega n by omega n, which means omega n will cancel out and you will get cos phi equal to zeta, and that is how we had defined phi, if you remember. So, this angle is your phi. Okay. So, here is something to think about, you think about it. Okay. If I increase this phi, if this pole comes to this point, the phi will increase, right. if I increase this phi, am I increasing the damping ratio or decreasing the damping ratio? Think about it. This is something for you to think about. Okay, we will come back to this idea sometimes later in the course. Next is the critically damped case. So, in the critically damped case, you see zeta is equal to 1. So, if I put zeta equal to 1, the purely imaginary part here becomes 0. The only thing that remains is minus omega n. So, this would be minus omega n and minus omega n, because zeta equal to 1 in this case. So, this zeta is 1, I could have just directly written minus omega n instead of minus zeta omega n. So, read it as minus omega n, zeta is equal to 1. So, this is the critically damped case. So, basically the system will be critically damped if the closed loop poles of the system. Why am I calling it closed loop? Because the transfer function of the plant here is this. Okay, this is not the closed loop system. So, I am finding out the transfer function of this entire system using this formula. This is the closed loop system. So, this is the closed loop transfer function. I have already told about these nomenclatures. So, I am just repeating it so that you do not forget these terminologies, because these will be used quite often in these lectures. Okay, great. So, what did you get? If the system is undamped, then the poles are on the purely imaginary. If the system is underdamped, then the poles are on the complex part. Basically, it is not either purely imaginary or purely real. It will have some real part as well as complex part. So, if the system is critically damped, then both the poles of the system would repeat at the same point and their value is minus omega n. And in case of overdamped, you will have both the poles on the real axis. Okay. So, if it is overdamped, then zeta is greater than 1, which means 1 minus zeta square will be a negative number. So, j and j you can take out a j from there. So, they will cancel out, and as a result you will get these two terms as the location of the closed loop poles. So, what we have seen is that for different location of the poles, closed loop poles, the response also changes. So, if I have to summarize, what did we see? What we have seen is that if your closed loop poles are on the purely imaginary axis, then the system is an undamped system. Closed loop system is undamped. That means the output will always have oscillations in it. If the closed loop poles are on the complex part, so basically it has a real part as well and a non-zero imaginary part as well, then the system is underdamped. So, basically it will oscillate, but the oscillations will damp down. Third case was if the poles are repeated on the real line, at the same point you have two poles, then the system will become critically damped. And now, if the poles are only on the real line, not even repeated, just on the real line they are located, then on the real axis they are located, then the system is overdamped. Okay. So, you can see that things which dependent on zeta. So, basically the response dependent on the damping ratio, right. Now, the response is depending on the pole locations also. So, from the pole location positions also I can say how the system will behave. This is similar to the first order case. Remember, in the first order case the pole location position was 1 by t, right, 1 minus 1 by t was the pole. So, when we changed the pole, the response changed. But in that case there were nothing like overshoots and all those things were not there, right. So, we did not divide the response into these 4 types like damping, non-damping. So, it was only one type of a response because it was an exponential trajectory, 1 minus an exponential function, right. But in this case there is a variety, because it depends not only just on one parameter, it is depending on zeta as well as omega n. So, we have divided the response into 4 types, that is why. Okay. So, now if I give you an example, in this example I am asking the question, is the closed loop system given below or underdamped or overdamped? So, you can find this out in 2 ways, either by finding out the pole locations or by pole location of the closed loop system, not the open loop system, or by finding out the zeta values. So, in this case if I ask you is it underdamped and overdamped, and you go ahead and just check this Planck's transfer function. Oh, the Planck's transfer function is 16 by s square plus 1.6 s. So, if 16 by s plus 1.6, oh, the pole locations are 0 and minus 1.6, and then you say that, oh, these are poles on the real line, real axis. So, this is a overdamped system. No, that is not how it works. We are not talking about the plant here. We are talking about the entire system, the closed loop system. So, this is very important. For which system are you asking about the response? If the question was, is the plant here underdamped or overdamped, then only you will look at the plant transfer function and then look at it. Okay. But here we are not talking about just the plant, we are talking about the entire system after you have connected the feedback also. So, the closed loop system is underdamped or overdamped. So, for that you will just have to find out the transfer function of the system. So, here I have written this as C, you can write it as Y also. I mean, yeah, the nomenclature should have been the same, but it is fine. I mean, it's just a variable, so I am naming it C in this case. So, C by R is 16 by S square plus 1.6 S plus 16. So, if you go ahead and see the pole locations, the pole locations will come out to be this, and since these are complex pole locations, complex as in non-zero real and non-zero imaginary part, so this will be an underdamped system. The second method is, okay, the second method is just find out the zeta value. So, you see this is a standard transfer function, right, because the standard transfer function was for a second order system was this. So, I can directly compare this and this. So, if you directly compare this and this, so what will you get? You will get omega n square equal to 16 here. So, which means omega n is 4 radian per second. Remember the unit is radian per second because omega n is a frequency here, right. Omega is 4 radian per second, and the damping ratio in this case will come out to be 0.2 because this is 2 zeta omega n. So, 2 zeta omega n equal to 1.6 and you do the calculations, you will get 0.2. Now, damping ratio is a ratio, so it does not have a unit in it. Okay. So, this is this is how you can actually directly find out whether the closed loop system is underdamped or overdamped. Now, let us look at the case when we add a controller to it. Remember, for the first order case also we had done something like that. We said that okay, we have the system, now we add the controller and can I change the pole locations. And for this case also you will see, let us try to find out the transfer function of the system. So, the overall transfer function of this system will come out to be Ys by Rs is equal to k omega n square by S into S plus 2 zeta omega n, because this is Gs in this case. So, the Gs is product of these two now, 1 plus G is k omega n square by S into S plus 2 zeta omega n. So, finally, what is the expression we get? The expression we will get is k omega n square divided by S square plus 2 zeta omega n S plus k omega n square. Now, notice this is not in the standard form because our standard form had an omega n square here and then we had something like this, right. This was omega n square fine. Okay. So, in this case if I have to make it omega n square form, so this is what our new omega or the natural frequency is. So, let me just write it down. So, I can write it down like this. Okay. So, now then I have to write the omega here as this. So, I can rewrite this as zeta by root k. So, let me just write it down again, 2 into zeta by root k into root k omega n s. See, this expression and this expressions are same. So, what have we done here? Notice, very importantly notice here. So, using this k, what you have done is, if you keep k equal to 1, then I exactly get back this transfer function, right. This is the standard case. Now, if I vary k, see, so this is my new damping ratio. I can consider this to be the new damping ratio and this is my new natural frequency. So, by changing k, I am changing the damping ratio and the natural frequency as well, right. And how does it affect us? It affects us because if you remember, what was the poles of the standard system? The poles of the standard system was minus zeta omega n plus minus j omega n root over of 1 minus zeta square, right. This was for the standard case. Now, for this case, what will be the poles? Minus zeta dash omega n dash plus minus j omega n dash root over of 1 minus zeta dash square, right. This will be the new location, new pole location, and you see here zeta and omega n dash are being changed by k, which means I am able to change the location of the closed loop poles using this k. And this means, suppose something is underdamped, you can actually change the closed loop pole locations and make it overdamped also. So, by changing the location of the value of k. This is similar to what we did for first order case. In the first order case also, by changing the value of k, we were changing the location of the poles and as a result the response of the system was changing. In this case also, by changing the value of k, I can change the location of the closed loop poles and the response of the system. Okay. So, here is another thing for you to think about. Okay. I will bring these small questions and I will put these seeds as we go along in the lecture, and I hope you will be able to answer on your own. What if this system that we have was the quadrotor system that we had? Suppose this was 1 by s square. Then my question is, can I use k? Can I use k to place the or change the closed loop poles of the system in such a way that the system's overall response is underdamped? Think about it. I am not going to straight away answer it now or in the next lectures, but I will bring this somewhere down the line in one of the lectures, and I want you to think about it till you get to that lecture. Okay. So, I will end this lecture here itself, and then we look into something called time domain specifications or specifications of a second order closed loop system. Thank you.